It's a very important problem in statistics because basically we do many things. We estimate many quantities via averaging. And when you average a number of observations or measurements, you basically sum them and then divide by their number. So the issue of summing random variables and then scaling them perhaps by dividing them by their number n or by the square root of n and so on is very fundamental, as we'll see in, again, it's in probability and statistics. This is like a very useful and widely used problem. So our starting point will be basically the sum of just two random variables. Suppose that these two random variables are absolutely continuous. So last time what we did is that we obtained the CDF, and then using Leibniz rule for differentiation under the integral sign, we differentiated the CDF to obtain the PDF. And the PDF of z, which is x plus y, is given by this integral here, or that integral. And so you take the joint. You take the joint of x and y, and one way of doing things is to keep x, and so this will be your dummy variable of integration, but then to replace y in the joint PDF of x and y, you replace y by z minus x, and then you integrate with respect to x. You end up with a function in z, and this will be the PDF of the sum. And now, if x and y are independent, then their joint distribution can be written as the product of the marginals. And so this guy here can be written as fx of x, and then we have f of y z minus x. So we get basically this sort of a bit more simple integration to do, and this integration here is basically the so-called convolution integral. And generally, if we have two functions, let's say eta of alpha and gamma of alpha, and we want to convolve those functions, so what we do is that we basically choose a dummy variable of integration, say beta, and then we take eta of beta, and then we get gamma of alpha minus beta. Okay, so again, this is a standard convolution in mathematics, and it has, again, many applications, but it's not important like to recognize that this is a convolution. If you don't know convolution, it is just this integral here. And of course, so you need to use this integral if the two random variables are not independent. If they are independent, then you can go for this integration here. Now let's take an example. Our two random variables are uniform 0, 1, and so basically their PDF is the indicator from 0 to 1, and we want to basically apply the formula. They are basically independent now by the problem statement, and so we can apply this formula here. Now, one way of doing things is basically to just put the PDFs inside the integration and integrate, but it is always important, like if the PDF is like, sort of defined on, on a region or something like this, it's better actually to keep it with the indicator function. Sometimes this, will allow you to basically write down correctly the limits of integration. So here the PDF, I mean, it's just one. I mean, the PDF of this thing is one, but it's not one everywhere. One everywhere is not a PDF to begin with. It is one on the interval from 0 to 1. So that's basically the indicator here from 0 to 1. So f of x will be the indicator, and x is living between 0 and 1. Now, the other indicator, so f of y basically is an indicator that is also small y is between 0 and 1. Now, according to the rule for finding the PDF of the sum, what we do is that we go to this y and we replace this y by basically the the quantity z minus x. Okay, so the PDF of y evaluated at z minus x will be the indicator z minus x now living between 0 and 1. Now, the first indicator is like sort of straightforward to interpret. So basically, the first indicator tells you that x is lower bounded by 0 and is upper bounded by 1. The second indicator, tells you basically other inequalities regarding x. Okay, so you are computing this for z. So think of z as fixed. Now, basically, this other indicator tells you, for example, if you take z minus x is greater than 0. If z minus x is greater than 0, then this means that z is greater than x. So Z is also another upper bound on X. So this indicator tells you that X is upper bounded by 1. This indicator tells you that, X is also upper bounded by Z. But you can also study this inequality here, which is Z minus X is less than 1. And this, if you move minus X to the other side and 1 to the other side, here we get that X is greater than Z minus 1. So that's another, this indicator function. This indicator function is 1 if X is greater than 0, and this indicator function is 1 if X is greater than Z minus 1. Note, of course, that the parameter small z is living between 0 and 2. Why? Because you are adding two random variables. Each one of them has the range of values from 0 to 1. So basically, the range of the sum, is almost surely between 0 and 2. How can you get a negative number? I mean, you are summing two non-negative quantities, you cannot get a negative number. And then you are summing two quantities, each one of them is upper bounded by 1, so you cannot get a sum that is greater than 2. So basically, small z is living between 0 and 2. So again, let's the indicator functions are 0 if their conditions are not met. If their conditions are met, then we have the following. We have x should be greater than 0, and also x should be greater than z minus 1. Okay. Basically, for the integrand to be equal to 1, not 0, you need both indicators to be 1 at the same time. So you need all these inequalities to be satisfied simultaneously. If x is greater than 0, x is greater than z minus 1, then, so x should be greater than 0, should be greater than z minus 1, then it should be greater than the maximum of these two guys. Okay, the maximum of 0 and z minus 1. Now we have two other inequalities, which are basically that x is upper bounded by 1, and then from this indicator x is upper bounded by z. Then if x should not exceed 1, it should not exceed z, then it should not exceed the minimum of them. So x is less than the minimum of z and 1. Okay, and so our integral now becomes the integral of 1. Again, 1, because it's basically we focused on the values of small x that will make the product of the two indicators basically equal to 1. So the integrand now is 1, and the integration limits are from max 0 z minus 1 and min z and 1. And you can basically, evaluate those integrals. So you can divide into two cases, right? So you have minimum z and 1. Okay, so what is this quantity? Is it z or is it 1? Well, it depends on the relationship between z and 1. So, basically, it may be nice here to basically divide into two cases. The case in which z is greater than 1. Okay, so if z is greater than 1, so it is from 1 to 2. We know that it cannot exceed 2. If z is greater than 1, then the minimum of z and 1 is 1. Okay, because z is greater than 1. And if z is greater than 1, then z minus 1 is positive, and so the maximum of 0 and z minus 1 will be z minus 1. Okay, so this will be, in this case, if z exceeds 1, then the integration is from z minus 1 to 1, and so basically the result will be the upper limit minus the lower limit. Okay, now if z is less than 1, and of course it should be non-negative, then if z is less than 1, then z minus 1, then z, minus 1 is a negative, 0 or negative. If z is 1, it's 0, then otherwise it's negative, and so the maximum will be 0. And if z is less than 1, then the minimum of z and 1 will be z itself. And so in that case, you will find that the upper limit is z and the lower limit is 0, and the integration, because we are just integrating one constant 1, then the integration is the upper limit minus the lower limit, which will give you z. Okay, so this is basically the PDF of the sum of these two RID U01 random variable, and you can combine it like with this indicator. It's Z, the PDF is Z from 0 and 1, and it's 2 minus Z from 1 and 2, and which is this triangular PDF. Okay, and again, for those of you who know convolution, basically when you have like these two, it's like rectangular pulses. Like if you plot this thing, it is 1 from 0 to 1. Then we know like a rectangular pulse with a rectangular pulse. When you convolve them, you get this triangle. But again, you do not need like to know these things. You can just do the integration. And again, I will, I'm repeating myself. It is advised that you keep the indicator functions and take them very seriously. Okay, it's it's very difficult like to keep the limits of integration or to get the limits of integration correctly. With the aid of the indicator function, you can basically in a systematic way find the correct limits of integration. Okay. Now suppose that you will have that W. W is Z plus another independent uniform 0-1 random variable. Okay, so what will be the PDF of W? So you need to do another convolution, right? So PDF of W is basically the integral. It's the integral of now f of z. Okay, so it will be f z, and then we basically take the uniform, so it will be indicator, and then W minus Z 1, okay, and then dz. Okay, so my point is that if you have more than 2 random variables, you start to repeat this. So you take two guys, and you get the PDF of the sum, and then you take this PDF of the sum and repeat the same operation with the third PDF, and then you get the sum of those 3 guys, and you repeat the operation with the 4th PDF, and so on. It does not seem to be a nice procedure at all. Okay. And so this is, let me say it from here, that this will be a motivation for something else. Like if we want to study sums of random variables, again, because they are very widely used and very useful, then we need a technique that actually makes the management of sums of random variables much more basically convenient. And the tool for doing this will be something that we will study later in the course called the characteristic function. So the characteristic function, again, if you know system theory and so on, it's a characteristic function is like the Fourier transform, and Fourier transforms have this nice property is that they convert convolutions, which are integrals, into just products. Okay, and so we'll talk about this. So actually, one big motivation again for going beyond PDFs and CDFs and so on, that those guys are nice and so on, but again, they can be very hard to manage when we talk about something like sums of random variables. Then we switch to something else, and this thing will be the characteristic function. Okay. Yeah, I mean, if you have 4, then you can take the first 2, and then the second, and then the second 2, and then do. Yeah, you can do it. It's you will save yourself one extra integration. But the idea is the same. That this is difficult. In fact, like when we study, we will actually be interested in like sort of limiting cases in which like if big N, if the number of random variables is very large. Right, so take limits and so on. So so whatever you do, I mean, the process of just doing these integrals will not be helpful. Okay, but of course it's something to keep in mind, and you can use it like in easy cases. Okay. Now, since we talked about the PDF of a sum, then you can start like talking about like the PDF of any binary operation between 2 random variables, right? The difference, the product, the division. Okay, so let's talk division. I mean, it's basically you will get the idea. So I mean, so you can take 2 random variables and do anything to them. And so what if you just divide them, x over y? So what is the distribution of the ratio? So here we are assuming that basically that y is not 0 almost surely. Okay, so the probability that y is equal to 0 is equal to 0. Okay, which is satisfied if y is a continuous random variable, right? If y is a continuous random variable, by definition, the probability of y basically belonging to any Borel set of Lebesgue measure 0 is 0. Okay, so this will be satisfied. Now, again, our starting point will be the joint PDF of these two guys, X and Y. We are interested in the PDF of the distribution. So as in the case of the sum, let's start with the CDF first. CDF, okay, so the CDF, it's basically the probability that big Z is less than or equal to small z, and big Z now is X over Y. And now, there is a bit of, it's a bit more difficult than the summation case. The reason is that, like, you have this inequality here, and like if you won't write it, like X is less than, X and on one side and Z and Y on the other side, if you want to multiply by big Y, now you are basically you have to deal with two cases. Because if Y is negative and you multiply by Y, then you have to reverse the inequality. Okay, so basically the idea here is to apply the law of total probability and say, no, basically we can have X over Y less than or equal to Z, and then we have two situations. We can have Y is positive or Y is negative. Okay, because they make a difference. If you multiply by Y, if Y is positive, you multiply the inequality both sides by Y, the inequality is preserved. So the direction of the inequality will not change, but it should be reversed if Y is negative. Okay, so this is the idea here, is that you say, okay, this event here is basically the event, the same event, and Y greater than 0, or the same event and Y less than 0. There are no other possibilities, again, because the probability that Y is equal to 0 is 0, and which is satisfied, for continuous random variables. Okay, so now you can multiply by Y, and so when Y is positive, the inequality becomes, it's the same in the same direction. So X is less than or equal to small z and Y. But if Y is negative and you multiply both sides of the inequality by Y, then you have to reverse the direction of the inequality. So this becomes big X greater than or equal to Z small 1. Okay, so this is the. Yes, we are because we are basically continuous random variable, or generally you want this to be certain. You don't want Y to take with a positive probability to take the value 0, because actually this will cause you trouble in the definition of X over Y itself. So if there is a strictly positive probability that Y is 0, then there is a strictly positive probability that you are dividing by 0. Okay, and so, then Z will be like infinity minus infinity, something like this. For now, our random variables are not allowed to take the value. They are basically a function or a map from the sample space to the set of real numbers. And the plus infinity and minus infinity are not real numbers. Okay, so yes. Okay, so that's the reason, we should have that, the case of 0 is actually the probability is 0. Okay, now, you start doing things like in the case of the sum, so I do not want to waste more time on this. So basically, if you have probabilities involving two random variables, again, sort of, if you want to do things carefully, you may plot. So you may say, okay, so let's plot the XY plane. Let's have the XY plane because our random variables are X and Y. And let's see, what are we doing? What is the event of interest in this integral here? So the event of interest here will be Y greater than 0, right? So if I just do it like this, so X and Y, so Y greater than 0, so we are here. Okay, so this is basically Y greater than 0. But it's not the only thing. We also have that X is less than or equal to zy. X is less than or equal to zy. Okay, so I mean z, it can be positive or negative. You can draw it anyway, but you will get the correct result in anyway. So if you assume that small z is positive, then X is less than or equal to zy. Draw the line X is equal to zy. So basically, this will be a line, okay, like this, in which the equation is X is equal to zy. Okay, so this will be a line with a slope 1 over small z. Okay, suppose that again the probability of this, that z is 0 is 0. Okay, and then we need x to be less than this guy here, okay? And so this will be this region here. So we want x to be less than or equal to zy, this one here. Okay. And then the intersection, right? Because we have this comma, as I said, it's like and, it's and so basically you need to integrate over this part here. Okay, so it's again y should be positive, what should be positive, and you should stop at this line, which is x is equal to zy. Okay, and so if we want to do this integration, we are integrating PDF. So by Tonelli, we can do the order any order of any choice. So we can basically integrate first with respect to x, then with y. Y is any number from 0 to infinity. Here, for this case, y is positive. Y is positive. Okay, and so y will go from 0 to infinity. Now fixing y, what is the range of x? So now suppose that y is fixed at some value here. What is the range of x? So x will go from it comes from minus infinity and then till it hits this line here. Okay, so x will go from minus infinity till it hits the line, and basically if the line has big Y equal to small y, then basically this point here, its x coordinate will be small z, small y. Okay, and so this will be your integral. Okay, so again, you want any probability involving two random variables, then you draw the two-dimensional plane, two axes, x and y. You can make x vertical or horizontal. I mean, basically, you should get the correct result in any, doing it in any way. And then for visualization, you may basically say, okay, so what is the region I am integrating over? And then you get your limits of integration. Okay, and you do the same thing here. Now you need to do Leibniz rule. So I did it last time for the sum. It's the same story here. You will basically do it 2 times. Okay, 2 times to the outer integral and then to the inner integral. Okay, and then you can find that basically these two integrals can combine to give you this final result. So the PDF of x over y, it is the joint PDF. And then you need to multiply by the absolute value of y. Okay, so this is the PDF x, z is x over y. Then you take the joint PDF, you replace x by zy, you keep y, and you multiply, as I said, by the absolute value of y, and then you do the integration. Okay, so it's even more a complicated integral than in the case of the sum of two random values, but it's doable. In some cases, basically, this is the formula to go. Okay, and needless to say that if the two random variables are independent, then you can, basically write the joint distribution as the product of the margins. Okay, so one of the classical examples of ratios of random variables, what if you take the ratio of two standard Gaussian random variables, zero mean and unit variance? So basically, in this case, this is the standard Gaussian distribution, zero mean and unit variance. Okay, so here the equation of x is 0 and the variance of x is 1. Okay, and just apply the formula. So what will be the PDF of x over y? So it's integral absolute y. Then here we have the guys are independent, so we can apply this formula. Then according to this formula, you take the PDF of y. Here it is. Okay, so the PDF of y, this is the PDF of y, again, standard Gaussian distribution. And then you take the PDF of x here, and you replace x by zy. Okay, so again, basically, it's the same standard Gaussian distribution. You replace small x by zy, and so you get this thing here. Okay, and you find that your integral is, you have in the exponentials, you have y squared, and then here you have the square, the absolute value of y. So basically, if you integrate an even function, and it is integrable from minus infinity to infinity, then you can basically take double the integral from zero to infinity. You do the integration here. You can basically have this y dy is equal to half dy squared. Standard integration, and you will get basically the result 1 over pi 1 plus z squared, which is the standard Cauchy random variable. So N01. If you have a standard Gaussian over standard Gaussian, and they are basically independent, then the distribution of this ratio will be the famous Cauchy random variable, okay? Cauchy, standard Cauchy, which basically has this PDF. Let me remind you of something, if you do not already know it, that basically when we talked about the first moment of random variables, we talked about the Cauchy random variable. It is an example of a continuous random variable in which the first moment does not exist. Okay, so remember, to compute the moment, you have x plus and x minus, and basically if each one of these two guys has an infinite first moment, then we say that our original random variable here will Cauchy random variable, it does not have a first moment. So the Cauchy random variable is like sort of a wild random variable. So it's an example of an absolutely continuous random variable in which the first moment does not exist, the second moment will be infinity, third moment does not exist, and so on. So the odd moments that do not exist, the even moments will be equal to infinity, because even moments always exist, because if you take a random variable, raise it to an even power, it becomes a non-negative random variable, and for non-negative random variables, the first moment always exists as a finite real number or as plus infinity. The Cauchy random variable is also nice in the sense that it is an example of a stable random variable, and again we will talk later about stable random variables. So basically it belongs to the same family of Gaussian random variables, and it's a family of nice distributions that obey a certain relation when you sum versions of them together. Again, we'll see this later, and these things are better studied using the characteristic function. Okay, but from here, keep this in mind. It's a very useful piece of information. Standard Gaussian divided by standard Gaussian has the distribution of a standard Cauchy random variable. And this standard Cauchy random variable, it is this example of an absolutely continuous random variable without a first moment. Okay, so basically this is Z is in R. Okay, so this is Z, from minus infinity to infinity. Okay. Let's go now to I started this chapter, by basically having some random variable x and then applying a function to x to get y. Okay. Then we talked about what if you apply a function to a bunch of random variables to get something, one single random variable. Like what if you have x and y, and you are interested in the PDF of the sum, or what if you have x and y and you are interested in the PDF of x over y. Now what if we have n random variables, and from them we generate new n random variables, and we want to find the joint distribution of the new n random variables. Okay, so now suppose that again you have our random variables so you have like a random vector x, and its components are x1, x2 up to xn. Okay, and now what we do is that we have big N functions, g1, g2, g up to gn. And what we do is that we apply g1 to those n random variables to get the new random variable z1. We apply g2 to those same n random variables and get z2. And then we apply gn to the n random variables and get zn. So we are doing a transformation from zx with those n random variables as components of x. And now we have a new guy, z, and we have z1, z2, and zn. And again, don't forget that each one of those z's is some function applied to the x's from x1 to xn. Okay. Objective? What is the objective? What is the goal? Again, which is something that we, it's not a theoretical problem. It's something that, if you do signal processing, machine learning, communications, control theory, whatever. You find that you always have to deal with this problem. You have a bunch of random variables, and you transform them to new random variables via certain functions that appear in your problem. And assuming that you know the joint PDF of x1 till xn, now the question becomes, what is the joint distribution of basically those guys here? So the formula, so the proof of this formula is in the notes, okay, and you can read it. It makes use of the inverse function theorem. You know, it's you can skip it if it depends on, you know, if you are curious, you can just read the derivation. If not, you know, the most important thing to us, you know, I will not ask you about the derivation, but I will ask you about, you know, basically, you know, I will test whether you can use this formula. So using it, learning how to use it is for now is more important than the derivation, but the derivation is there for completeness in the notes. Also in the notes, right, you will find one page on basically justifying why something like, if you have two random variables, x and y, then x plus y is itself a random variable. Again, I am saying this here, I said it in the lectures as if it's like effect of nature. You know, that if you have a random variable x and then you have a random variable y, then when you sum them together, you get a new random variable, okay? But who says? I mean, how can we be sure about this? So there is one page in the notes in which like there is a rigorous justification of why the sum of two random variables is indeed a random variable. Okay, so remember, random variables should be f measurable functions. So it's an optional page. You can read it if you are interested, or you may skip it. For us, as I said, we will, you know, the common functions that are employed in practice, we will take, you know, that whenever we apply those functions to random variables, we get random variables. Okay, so we'll not like need to worry about this. But of course, like if you do things very rigorously, then no, I mean, it's not clear why if I add two f measurable functions on a sample space that we are guaranteed to get an f measurable function. We don't know, right? So there is a proof for this. Okay, but again, you can ignore it. Back to business here, you have n random variables, and from them you generate new n random variables, and basically your result will be a summation. Okay, so your result will be a sum over terms. Okay, and it will include the Jacobian matrix. Okay, so let me show you what is the Jacobian matrix. So before even explaining the summation, so I mean, you may have seen this before in, you know, maybe in some course on probability or like multivariate calculus or whatever. So by this, if I have like this sign of partial and then z1 to zn, and then in the denominator we have x1 to xn, and with an absolute, this is the absolute determinant. So absolute determinant. So if you compute the determinant and you get like -2 or something that is negative, you should apply the absolute value. Okay, so so here we need to take absolute determinant of this matrix. And if you look at this matrix, so basically what we do is that the first row in this matrix is the partial derivative of z1 with respect to each guy here. So it is partial z1 with respect to x1, partial z1 with respect to x2, up to partial z1 with respect to xn. The second row will be partial z2 with respect to x1, then x2, then x3, up to xn, and so on and so forth. Okay, so this is, you know, again so this thing here is the Jacobian. It's called the Jacobian matrix. Okay, and you can actually have the x's here and the z's here, and in that case, again, you just follow the definition. The definition will be that you have a matrix, and this matrix will be, you take the first guy here. So how to construct your first row in the matrix? You take the first guy here and you partially differentiate it with respect to z1, z2, z3, up to zn. That's the first row. Then you take the second guy here, which is x2, you partially differentiate with respect to z1, z2, up to zn, and so on and so forth. And you know, the matrix itself is not what we need in our formula. We need not only the determinant of the matrix, we need the absolute determinant of this matrix. Okay. And so in the formulas you find this expression here again. You know, I'm sure that you have, you know, or most of you have seen this before. So as a reminder, this is basically the absolute determinant of the Jacobian matrix, and you can show that basically that that these two numbers, I mean, these are two numbers, one of them is the reciprocal of the other. And I think the derivation is in the notes. So you can have in the denominator the Jacobian written in this way, or you can have it in the numerator, so here it's downstairs, it's the PDF divided by, or you can have it multiplied by, but you need to use this form here. Why is this the case? Because this guy is 1 over this guy. And again, you can see it in the notes, or you can just take it for granted. Okay? Absolute determinant, very important. Okay, so this is basically the absolute determinant of the Jacobian. But what is the summation? What is the summation here? It's summation over what? So it is like in the single variable case. So in the single variable case, okay, we have a formula that looks like this. This is a generalization of the single variable case. So suppose that you are interested in the PDF of Z at a certain Z. Now Z is a vector of values, right? Z, small, this is small z. Big Z is not just one random variable. It's a bunch. It's a big N random variables. And so small z is basically like a vector in which like the first random variable takes the value small z2 up to Z big N. Now we are interested in obtaining the PDF of random vector Z evaluated at Z1, Z2, small z1, small z2 up to small zn. And so what we do is that we solve it. Okay, so you basically write down, you ask, what is basically, G1 equal to Z1, G2 equal to Z2, and then Gn equal to Zn. So you write down equations, and the summation here is a summation over the solutions to these equations. Okay, so I will assume that the solutions take this form. So basically, x superscript 1 it's a solution. It's some values of x1, x2 up to xn, such that if you apply g to those x's, you will get small z. Now, this system, it can be a system with just one solution, or it can have, actually, it may have no solution at all, or it may have one solution or multiple solutions. So the summation here is a summation over all possible x values that are mapped with function g to give you the vector small z1, small z2 up to small zn. And what you do is that you take the joint PDF of big X1, big X2 up to big Xn, and you put in the solutions to this system of equations. Okay? Now this seems very obscure, and this is like one case in which you really need to see examples. It's like just saying it abstractly is sort of not enlighten. It does not enlighten you at all. Okay, this thing is best seen like implemented. Okay, so and let's start with the most simple like transformation from x's to z, which is linear, because like if the g functions are linear, like you have linear equations, so they are like more manageable. Okay, so let's do it now. Example 1. Suppose that this is how you generate your z's. Okay, so z1 again is g1 of x1 plus x2. This is the general formulation. z2 is g2 of x1 minus x2. Now x1 comma x2, this is x1 comma x2. So g1 is some function. It can be a very complicated function, by the way, of x1 x2, but in our case it is just the simple function. You just sum the two guys. Now z2 is another function of x1 and x2, and let's say that we will just take the difference of the two guys. Okay, the difference of the two guys. Okay, so now what we do is, let's start with the Jacobian. So again, you have two forms. You can compute this Jacobian matrix or that Jacobian matrix, and then take its absolute determinant. Sometimes this is easier, sometimes this is easier, sometimes they are, the level of difficulty is almost the same, and you can go for any one of them. So here what I will do is that I will rewrite x1 and x2 as z's. Okay, so I will take these two functions. Okay, so if we add z1 and z2, we get z1 plus z2 is equal to 2x1. And if we subtract, okay, we get z1 minus z2 is equal to 2x2. Okay, so x1 is 1/2 z1 plus 1/2 z2, and x2 is 1/2 z1 minus 1/2 z2, which means that if I give you specific values for z1 and z2, what are the x's that will produce these values? They are very specific x's. Okay, so x1 will be 1/2 z1 plus 1/2 z2, x2 will be 1/2 z1 minus 1/2 z2. Okay, and this is a system, again, this is a system of linear equations that is guaranteed to have one unique solution. So if you fix z1 and z2, again, you have a system of linear equation that looks like this. Okay, so fixing z1 and 2, we have like x1 plus x2 is equal to z1, x1 minus x2 is equal to z2. The determinant of this system will be 1, 1, 1 minus 1. So it is equal to minus 2, which is not 0. So this system has a unique solution as linear equations. Okay, so it's a system with unique solution. And what is the solution? Actually, this is the solution. Easily you can get it here. Give me z1, z2. Their average is x1. Their difference divided by 2 is x2. Okay, so again, you know, this is some. I mean, sometimes these things can be complicated. Z1 can be like x1 squared plus exponential x1. So we can have things that are more complicated. But in this case, we can say that actually we have a unique solution. Give me z's, I can give you, you know, the x1 and x2 that gives you those particular values for z1 and z2. Now, what is the Jacobian matrix? So the Jacobian matrix, again, let me write it explicitly. So you take x1, if you want to form this one, x1, the first row will be x1 with respect to z1, x1 with respect to z2, and the second row will be x2 with respect to z1, and then x2 with respect to z2. Okay, so this will be the Jacobian matrix. And so in our case here, this partial derivative will be 1/2, and this one will be 1/2. The second one, x2 with respect to z1 will be 1/2, and x2 with respect to z2 will be minus 1/2. And so this is the Jacobian matrix. So the determinant is 1/2 times minus 1/2 minus 1/2 1/2. So this is minus 1/4 minus 1/4. So it is minus 1/2. And so this is the absolute determinant. Remember that what we need in the formula is not the determinant, it is the absolute determinant. The determinant of the Jacobian matrix as written will be minus 1/2. The absolute determinant will be 1/2. Okay, so this will be this term here. Now in our case, because if you fix z's and obtain the solutions, you get just a single solution. So our summation is just one term. Okay, so we don't really have a summation. It is just one term, again, because in our first example, for a given z1 and z2, we have, you know, a single solution, a unique solution. Okay, so we will not have summation, or like, let's say we have a sum with just one term, and then we have the absolute determinant, that is 1/2. So that's the absolute determinant. And then what we need to do is to use the joint PDF of x1 and x2 and write it in terms of the solution. What are the x1 and x2 that give you a particular small z1 and small z2? And this can be seen directly from here. That basically, given small z1 and small z2, you know, x1 will be the sum over 2, their average, and x2 will be the difference divided by 2. And so this is the general result. So if I give you two random variables, and you do not have these two random variables to be independent or anything, this is the general result. You take the joint distribution, you replace, you take the first x random variable, x1, replace it by small z1 plus z2 over 2, x2 is replaced by z1 minus z2 over 2, and then do not forget to multiply by the absolute determinant of the x's with respect to the z's, which is computed like this. No, I mean, sometimes, yeah, it depends. You know, sometimes you have infinite number of solutions, and basically the sums, the sums converge. Yes, you can have an infinite number of solutions, because like you can do things like you can do things like basically using a function that, like, let's say sine or cosine or something like this, that will take many, you know, infinitely many values of some x and gives it. And this is actually also in the one-dimensional problem. So it's also applicable to the one-dimensional case. Now, is this summation, you know, will the PDF we get from the summation make sense if we have an infinite number of solutions? You know, in many, you know, the problems that we'll study, it will make sense. Okay, so I mean, don't worry if you have an infinite sum. You know, in the problems of interest that appear in applications, typically these things they yield a finite result. But do you have the problem of you know, running into something, you know, that causes mathematical problem? Of course you can do. Same story again. I said it in the previous lecture. You know, I didn't say it in this lecture, but it's also worth mentioning that when we get the PDF from the CDF. So here, this formula gives you the PDF directly. But what if you use like something like obtain the CDF first and then obtain the PDF? Well, in that case, you will have to do differentiation. And if your CDF is in terms of an integral, then you will have to use the Leibniz differentiation under the integral sign formula. You can search, you know, for counters. This formula, yes, it can fail. You know, it's not correct all of the time. But for our purposes, you know, it will work, and so you don't need to check them. Okay, so again, let's put it this way. For pragmatic reasons, our focus here in this course is how to use these tools to get distributions. So I will never use a trick in which basically, you know, you have something, you know, a divergent sum or something like this. Okay, so the trick will be actually how to apply the formula, and sometimes it's not straightforward to apply, by the way. So we will just focus on this for this, you know, particular course, but we do not need even to justify. Okay. But yes, you know, can we have infinite number of solutions? Yes, because there are functions like sine and cosine, you know, that can take, at least some infinite value, an infinite number of x values to a specific y value, let's say. But you know, go for it. If you know, you can still use it here in this course. Okay. You can have like this is like the general solution. Can you solve this general case like for a specific case? Like what if x1 and x2 are IID exponential 1? Then what you need to do is just substitution, right? So if x1 and x2 are IID exponential 1, so what is the joint? What is the joint distribution? So basically each one is exponential 1. So you know, basically each one it has this distribution that is e to the minus x1, e to the minus x2, and each random variable is non-negative. And because they are independent, that's the first I, they are independent, then you can write the joint as basically the product. Okay, so in that case, what you will do is that you say so f of z1, you know, z2, small z1, small z2 will be half. Don't forget this one, very important. Otherwise, I mean, if you forget it, basically you will not get a proper PDF. Remember, a PDF should integrate to 1. So if you forget this 1/2, you know, you get nonsensical results. So 1/2, and then you have e to the minus. So here we have x1, x2. So this thing is e to the minus x1 plus x2, and then the indicators. Okay, what is x1 plus x2 by definition? It is z1. Okay, so it is z1, and then since you are replacing your variables, this is the thing I was talking about when, you know, we talked about, you know, the sum of two random variables and the ratio of two random variables. The indicator is important. Like, you know, some people will write just the exponentials, and keep in mind that the random variables are non-negative. You can do things totally in your brain, you know, and then write down the result correctly. You can do so if you can, you know, if you can get it correctly. I don't care about, you know, basically how you arrived at the correct solution. But sometimes if you want like to proceed carefully and make sure that you will not commit mistakes, is like keep the indicators. They are very important, because when you replace x1, say by z1 plus z2 over 2, then you should replace it everywhere in the definition of the PDF, including inside the indicator function, right? So it is not just that we'll take this x1 plus x2 and replace it by z1. This x1 is also replaced by z1 plus z2 over 2. and this x2 is replaced by z1 minus z2 over 2. So we have two new inequalities. So the inequalities in terms of the x's are very, it's basically the positive quadrant. X is non-negative, x1 is non-negative, x2 is non-negative. But when you do the transformation, when you apply the functions to obtain the new variables z1 and z2, now what we have is that z1 plus z2 should be positive, and z1 minus z2 should be greater than or equal to 0. Right? So now our first inequality, we want the sum to be positive. Okay, so again, if you draw, if you sketch a two-dimensional plane with one axis is z1 and the other axis is z2, then the line z1 plus z2 equals 0 will be this line with the slope -1, and the region in which the sum is positive will be this upper region. Now, if z1 minus z2 is equal to 0, that's z1 equals z2, so this will be the conventional line here with the slope 1. And if we want the difference to be non-negative, to be greater than or equal to 0, then this is the region where z1 minus z2 is basically greater than 0. Okay, and you can check it by just checking one point, right? So here you have the point 1, 0, and it satisfies the inequality. Okay, so if you are like confused which half plane, is it the lower half plane or upper half plane, just take one point in the plane, in the region, and see whether it satisfies this. Okay, so if it confuses you, are we this part or that part, just use one special point to tell the difference. Okay, now you need the intersection of these two regions, and so the intersection is this one. Okay, so now the indicator, basically your PDF of z1 and z2 is non-zero. So for the x's, it's non-zero over the positive quadrant. When x1 is greater than or equal to 0, x2 is greater than or equal to 0. But now for z1 and z2, it is basically over this part here. Okay, it is over this part here. Again, you obtain it by, keep the indicator function. Very useful to have them. When you do the change from x's to z's, do it also to those guys in the indicators, and then go and obtain your new basically region on which basically this PDF is defined. And now it is defined on this part here. Okay, and you find this part, like, it makes sense, because like if you have two non-negative random variables, z, x1 and x2, and if what is z1? So remember, z1 is the sum over 2. Now, if you sum two non-negative random variables, you are guaranteed to get what? You are guaranteed to get something that is non-negative. Okay, so z1 should be non-negative. So we do not expect basically to find to have a z1 that is negative, because z1 is the sum. Now, what about the difference? What about the difference between z1 minus z2? Well, x1 minus x2. So z2 is the difference. Now the difference, if you subtract a non-negative number from non-negative number, you have all possibilities, right? So you can get any number that is positive or negative or or 0, right? And then we have something else, that basically the difference between two non-negative numbers is always less than, is in magnitude less than or equal to the sum, right? So this region here, you can write it as the absolute value of z2 less than or equal to z1. And this is nothing but the triangle inequality, because z2, okay, z2 is x1 minus x2 over 2, and z1 is x1 plus x2 over 2, and it's non-negative random variable. And so basically what we are saying here is that absolute x1 minus x2 should always be less than or equal to, in our case here, x1 plus x2, because our guys are non-negative. So it's the triangle inequality. If you take two non-negative numbers, you take the absolute value of the difference. It must be less than or equal to the sum. Okay. So the fact that our PDF is in this region, I mean, it makes sense in terms of what we are doing. We are here taking the average of two non-negative random variables, taking their difference divided by 2, and so this is what we should have. But my point is that, rather than thinking like this, you take x1, x2, and then you can just follow your nose and use the indicator function. The indicator function will lead you to the correct region. Okay, but you can also, I mean, it's not, you can just, without anything, you can just do this. You can take e to the minus x1, e to the minus x2. We can combine these two guys as e to the as, you know, e to the minus z1 over 2. Sorry, I forget here, it must z1 over 2. Okay. And then, or 2z1, sorry, it should be 2. Z1. So, because, right, z1 is the, no, so here it's not 2 over 2. The x, the z itself, now, yeah, the x's are with the 2, this one is not with 2, so this is, okay, so it's the sum, no, so this is correct, actually. Okay, so the idea is that, again, you can basically do things without the indicator like this, x1 and x2, this will give you z1, this will give you z1, and then you say, okay, so now if x1 and x2 are both non-negative, then, you know, their sum will be non-negative, and then their difference in absolute value will always be upper bounded by the sum. You know, if you take this guy here, its absolute value can never exceed the sum, which is a manifestation of the triangle inequality. And so the region in which this e to the minus z1 is defined is simply this part here. Okay, so you can do it via like sort of this type of reasoning, or by follow your nose, which is like, you know, write the indicator and go with it. Go with it. Do the substitution and get everything from your indicators. Of course, you can use, you know, the mixed strategy. You can see that the problem is straightforward to you, and you can just do things without, you know, directly, or you may see that things are confusing and I'll employ the indicator. Okay. And of course, you know, knowing the joint, we can obtain the marginals, right? So, you know, if you know the joint distribution, you can just obtain the marginals by integrating over other guy, as we know from earlier. Let's take a more complicated example. So linear equations. So we're still linear, again linear because these are like sort of the easiest functions. It's a linear equations relating the z's to the x's, but now let's make things like a bit complicated by involving more random values. So here in this example 2, we go from x1, x2, x3, x4 to z1, z2, z3, z4, like this. And what are our functions? Z1 is x1. Z2 is x1 plus x2. Z3 is x1 plus x2 plus x3. And Z4 is basically the sum of the 4 guys. Okay, so you need the Jacobian matrix. You can have it in this form or in the other form, which is, so this is 1 over x1, x2, x3, x4. And then you have Z1, Z2, Z3, Z4 again. You can compute it this way or that way. If you compute the x's like in the previous example, you will have first to express the x's in terms of the z. In case of the linear equations, typically this is feasible. I mean, this is typically like easy to do. But here, I mean, to give you a flavor, just compute the Jacobian, the z's with respect to the x's. So remember, this thing here was a matrix. The first row, you just take z1 with respect to each single guy here. So z1 with respect to x1, z1 with respect to x2, z1 with respect to x3, and z1 with respect to x4. Second row will be z2 with respect to x1, z2 with respect to x2, and so on and so forth. Okay, so z1 with respect to x1, it's 1. With respect to x2, z1 does not depend directly on x2, so 0, 0, 0. So the partial derivatives of z1 with respect to the other guys will be zeros. Z2, its partial derivative with respect to x1 is 1, with respect to z2 is 1, with respect to z3, 0, with respect to z4, x4 is 0, and so on. So you get basically this Jacobian matrix. You take its absolute determinant. The Jacobian matrix here is lower triangular, and so basically the determinant is the product of the elements on the main diagonal. So it is basically the product of those ones, and this is 1. Okay, so the Jacobian will be 1. So that's nice. The Jacobian here, like the previous case, it's also a constant number. Okay, now now you need again to take again this system of linear equations. It has a unique solution. Okay, so it is a system of linear equations like the previous examples with a unique solution. Okay, so in our formula above, it's just one term in our summation. So in that term, we have the absolute determinant. Now the absolute determinant is 1. Okay, it was half in the first example. Now it's 1. Okay, fine. And then you need basically the PDF. you need to take the PDF with the x's replaced, written in terms of the z, because we want the function of those z's. So by the end of the day, we need to express the x's in terms of the z. And so here, z1 is x1, so x1 is z1. Okay, so that's nice. Now, what is z2? So from here, x2 is z2 minus x1. If we want to express each x in terms of a z, then from the first one, we know that x1 is z1. So this is z2 minus z1. z2 minus z. And then you come here, and you say, well, x1 plus x2, this thing is z2, and so x3 is z3 minus z2. And then you come here and say, those guys sum together, this is z3, and so x4 is z4 minus z3, which is this one. Okay, so in terms of in the x's in terms of the z's will be x1 is z1, x2 is z2 minus z1, x3 is z3 minus z2, x4 is z4 minus z3. Okay, and again, the absolute determinant is 1, and so this is basically the joint PDF. Now, in a problem, you may be given some distribution for x1, x2, x3, x4, and then you need to substitute. Okay, perhaps obtain marginals and so on. So again, so the problem can start with going from those 4 x's to those 4 z's, and then you may do something with the z's. Okay, and as we did earlier in the course. Now, let's take a situation in which basically the summation in this formula actually has more than one term. And let's make our functions a bit more complicated. So again, you start by linear functions because they allow you to basically digest what is going on here, but life is more complicated than linear function or linear equations relating the x's and the z's. So here let's go back to 2 random variables, but now we want the joint distribution between the sum and the product of the 2 random variables. Okay, so we have 2 new random variables. So we have omega is x plus y. Okay, so it's linear and fine. Now we have gamma, which is xy. So we have 2 random variables, x and y, and we are interested in the joint PDF of the sum and the product. So earlier we obtained, if I give you x and y, what is the PDF of the sum? Now we want the joint PDF of the sum and the product. Okay. So the challenge here, is basically to realize sort of a simple fact. Now, summation, if you sum 2 real numbers, summation, sum over r is commutative. And multiplication over r is also commutative. So if I give you a gamma and I give you omega and tell you what are x, what are an x and y, you typically get 2 solutions, right? Because you can swap. So let's give a concrete example. Suppose that x is 2 and y is 7. Okay, so gamma will be 14, right? And omega will be 9, right? But we get the same. We get the same if we swap x and y. If x is 7 and y is 2, right? Because if you interchange the 2 values, the sum is left intact and the product is left intact because, again, we are dealing with the field of real numbers, and for real numbers, sum and summation, addition and multiplication both are commutative. Okay, so this is the first thing to observe. In this problem, we'll have 2 terms in our formula, because if there is a certain x and a certain y giving you a certain product and a certain sum, then swapping x and y, giving the value of x to y and the value of y to x, will give you the will give you the same, the same result, right? So we have generally two terms. Okay. Now, what if like x is equal to y? If x is equal to y and we have absolutely continuous random variables, because if x is equal to y, now basically we have, we have like, if you swap, you get the exact same point. But if you have two absolutely continuous random variables, the probability that x is equal to y is 0. Okay, so you do not need to be obsessed by these things. Okay, so if x and y are, are jointly absolutely continuous, the probability x equals y, what is this probability? That random variable x is exactly equal to random variable y. Well, by the procedure.
It's the probability of a singleton.
Exactly. It's not a singleton. It's the probability of this line in the xy plane. It's the probability of. So basically, we say it's in. It's not just a point. It's a line in the xy plane. But this line, okay. This line, if you want to compute this probability, the line has Lebesgue measure, which you can think of as area 0 in R2, in the two-dimensional space. Okay, so this probability is 0. It's not an event that you need to really bother about. Okay, so again, it's a line. So it's like, again, like, very, very informally, what is like the area of the line? The area of the line, it's 0. And I think like in OneNote, actually, we did actually this Lebesgue measure of a line, and we showed that the Lebesgue measure of a line in R2 is equal to 0. Okay, and basically, if your event in the two-dimensional plane is a polar set with Lebesgue measure 0, the probability will be 0. This is like a famous event. Two absolutely continuous random variables, what is the probability that they are exactly equal? 0. Okay, so this is another point. So again, first point is that if you have two real numbers, and they give you a certain sum and a certain product, then you get the same sum, the same product by basically exchanging the values of these two numbers, because addition and multiplication are commutative. We don't need to worry about the two numbers being equal, because if our random variables are absolutely continuous, then basically the probability that x equals y is equal to 0. But there is something else. Okay, so again, this like problem, it's one of those problems that you need to step back and think for a while before starting to implement. So the third issue is there a relationship between the sum and the product of two real numbers? Okay, so again, if x assumes one of its values as a real number and y assumes one of its values, and is there a relationship between the sum and the product? And also, you need to think about this, that basically those are generally real numbers. I am not saying that the two random variables are non-negative. I didn't say that they are non-negative. Okay, so they actually, these two numbers, one of them may be negative, or both of them will be negative. So in fact, there is a relation, and you can see this relation in a number, in a number of ways. Okay. So one way is to apply the arithmetic mean geometric mean inequality to the absolute value of x and the absolute value of y. So this is one way. Another way is like what I did here, is that note the following. What if you take the sum squared minus 4 times the product? The sum squared, so take two real numbers and add them together, square, and then subtract 4 times the product. And here x and y can be any real numbers. They can be positive or negative. Well, just expand this bracket. So this bracket will be x squared plus 2xy plus y squared minus 4xy. Now, this minus 4 is not arbitrary. We have chosen it so that with the 2xy, this will give you, so basically this quantity here is x squared minus 2xy plus y squared. And this thing here is the expansion of x minus y squared. And x minus y squared, for any real valued x and for any real valued y, it's a square of a real number. And so it is greater than or equal to 0. So the sum of two real numbers squared minus 4 times the product of these two real numbers, this thing is always non-negative, regardless of what real numbers we are talking about. Okay, so again, the sum and product of two real numbers, they are related by this mysterious inequality. It must be the case that that omega squared, which is the sum, the square of the sum, is greater than or equal to 4 times the product. Okay, so this is the third point before proceeding. So again, let me recap. So you have sum and product. So first thing, if you have a certain sum and certain product caused by certain value of x and certain value of y, basically interchanging the x and y values will give you the exact same sum, the exact same product, because addition and multiplication on R are commutative. Number one. Number two, do we need to worry about x equal to y? Well, in these problems, typically our random variables are jointly absolutely continuous. The probability that x is equal to y is exactly equal to 0, because this event in terms of the R2 plane is the event of the line with the slope 1, and basically a line has loop measure 0 in the two-dimensional space. So basically the probability of this event is 0. We don't need to worry about x equal y. Third, is the relationship between the sum and product of two real numbers arbitrary? Is it like you take two real numbers, you can get any sum or any product? It turns out, again, you can understand it in a number of ways. This is one way I present here. No, you can show that basically it must be the case. It must be the case that the square of the sum is always greater than or equal to 4 times the product. Okay, so now we can solve, and now we know that our solution will have two terms. Okay, so we have here the summation. Again, what is this summation on? The summation is that you take the functions and you equate them to particular values here, and you solve. For examples 1 and 2, we have linear functions with unique solutions, but now you may get two solutions. Okay, that because again of this commutativity thing. Okay, so so here, here is one way of basically doing the problem, that xy is gamma, this is the product, and omega is the sum of the two guys. So you can take x. You want to express x and y in terms of omega and gamma. Okay, so again, in our formula we express the x's in terms of the z's. Okay, so here the x's are x and y, and the z's are basically this gamma and omega. So what is x in terms of gamma and omega? What is y in terms of gamma and omega? So x is gamma over big Y, because gamma is the product, and then you can take this x and put it in the formula for the summation, and then you can multiply both sides by big Y, and so y omega is equal to gamma plus y squared. So here we have just one equation in Y, and this equation, it's a quadratic equation in Y, and if you solve this quadratic equation in Y, you will get Y as a function of big omega and big gamma. Okay, so this is our quadratic equation. Y squared minus y omega plus gamma is equal to 0, and so big Y is equal to basically, again, we have the roots of we have two solutions, and basically the two solutions that you get, one of them is y, and if you take one solution and you take gamma over that solution, you will get the other one. So basically the two solutions with the plus and minus sign, again, you can check that their product will give you gamma, and so basically these are the two solutions that we have. And so our system, basically if you have xy equal to gamma and x plus y is equal to omega, now if you want to express what is x and what is y, this can be x with the plus sign and y will be with the minus sign, or vice versa, because the issue I told. So it's either x is equal to this with the plus sign and y with the minus sign, or you can swap. As I talked about earlier. Okay, so this is the relation between x and omega and gamma, y and omega and gamma. As you can see, this does not seem like, you know, like a nice relation, you know, because we don't have, no longer we have like linear, a linear transformation. We have this function here, which is nonlinear. You take x times y is equal to gamma. Okay. So we can basically do the Jacobian. So basically we have, you know, x. So this thing here is x with respect to gamma, x with respect to omega, and then we have y with respect to gamma, and we have y with respect to omega. And you know, we can do it for these two solutions of these two guys. By the end of the day, we will take the absolute determinant. Remember, we do not just take the determinant of the Jacobian matrix, we take the absolute determinant. In both cases, whether x is this and y is this, or basically x has this negative sign and y has the positive sign, in both cases, the absolute determinant will be this quantity here. Okay, that we have. Okay, so so now we go basically and apply the formula. This one. So the absolute determinant is 1 over, you know, this is square root of omega squared minus 4 gamma. And then we need the joint distribution of the two random variables in the problem x and y. And we need like to replace x and y by basically z. Our final objective is basically to get, you know, basically the joint PDF of the product and the sum. And so f of gamma and omega, and so we need to express x as gamma and omega, and now we have two terms. And again, for both terms, you can check by doing the absolute determinant that basically you get the same factor, and this is actually our result. And I think that here, at least, it's very important to have this indicator function to highlight the existence of a relation between the sum and the product of two real numbers. They are not, they are not related in an arbitrary way. They are related such that the sum squared is greater than or equal to 4 times, 4 times the basically the product. And maybe actually this is the challenging part about this problem. To basically to get this. That actually the two things are sort of related in some way that is not very clear from the equations themselves. If I give you two equations, x plus y, xy, then what? Okay, so that going back to my point, that's the reason. Like here, I don't care about. Yes, yeah. The order will not change. Yeah. So basically, here in the original formulation, I take z1, z2, z3 with respect to x. What if you write things? What if you write things like with different order? And I will tell you the reason. The reason is not difficult. If you interchange when you compute the Jacobian, if you call things differently, like what you said that you want to make it the distribution of omega and gamma. Then basically when you compute the Jacobian matrix, you are interchanging the two columns, right? And when you interchange the columns of a determinant, what happens? Multiplication by? When you interchange order of two rows or two columns while you are computing a determinant, you get what?
-1.
-1, exactly. And then the nice part here is that we are not really interested in the determinant, we are interested in the absolute determinant, right? Won't matter. It won't matter. Okay, so don't worry about these things. Okay, basically you can, so here it's like I took z1 to be gamma and z2 to be omega. I mean, can we reverse them? Can we reverse things when we compute the Jacobian? So don't worry. I mean, these things will will give you the final result will be the same. Okay. Okay, so transformation of random variables is very important. Again, you will see further examples in the homework and tutorial sessions and so on. It is something again that is sort of you need to practice, and sometimes it's very straightforward. Sometimes it's tricky, like this last example when we talked about the joint distribution of the sum and the product. Among the other things that are that really appear when you apply probability is basically the idea of conditioning of random variables on an event, conditioning of a random variable on another random variable, and so on and so forth. Okay, so again, rather than driving things rigorously and so on, the examples are what is important, and here I will basically explain via examples. Okay, so suppose you have a PMF, like you have Px, big X is equal to small x. You have a PMF of some discrete random variable. Now you want basically the PMF conditioned on an event that X is greater than A. Okay, so we are interested in the probability that X, big X, is equal to small x, but it's conditional on some event. Of course, I will choose this event to be an event with strictly positive probability that big X is greater than A. So now, what is this probability? Well, apply the definition of conditional, the probability, the conditional probability that we studied earlier in the course. So if you have basically the probability of A given B, remember, it's the probability of A intersection B divided by the probability of B. Go for it, right? So the probability, this probability is equal to the probability that X, big X is equal to small x, comma is and, is intersection, and big X is greater than A, this is the event we are conditioning on, and then in the denominator we divide by the probability of that event, and that's the reason we need this event to have a strictly positive probability so that we do not divide by 0. So what is this probability? The probability that big X is equal to a specific value, small x, and that big X is greater than A. Then we can write down this joint probability as we did earlier in the course as, so this is the probability that big X is equal to small x, multiplied by the probability that big X is greater than A, given that big X is equal to small x. Okay. Now, what is this probability? Now we are conditioning on the event that big X is exactly equal to small x, given that big X is exactly equal to small x. So here, you can write down the probability that big X is greater than A, given that big X is equal to small x, as the probability that small x, which is some deterministic value taken by big X, greater than A, given that big X is equal to small x. Okay, so if I ask you what is the probability that big X is greater than A, given that big X is equal to 5. Well, it's the probability that 5 is greater than A. Now, those guys are deterministic. And so this probability that we have here is simply an indicator function. It's either 0 or 1. So you compare small x and A. If small x is indeed greater than A, then this is 1. If small x is less than or equal to small a, this is 0. So the probability that small x is greater than A, given that big X is equal to small x, this thing again is indicator x greater than A. So again, this probability here is equal to 1 if x is greater than A, is equal to 0 if x is less than or equal to A, which I can capture both cases by this indicator here. Okay, so now we have a nice result. So let's basically write it that now the probability that some discrete random variable big X is equal to small x, now given this event that x is greater than A, so we have some side information. Someone told us, that for some reason our random variable must exceed A, then this probability, now this conditional probability, will be the probability that big X is equal to small x. Okay, indicator small x greater than A, which makes sense, by the way, because if you condition that big X is greater than A, and this value small x is less than or equal to a, then this thing should be equal to 0. What is the probability that big X is equal to 7, given that big X is greater than 9? 0. If you know that big X is greater than 9, and I ask you what is the probability that big X is equal to 7, 0, because it's given that big X is greater than 9. So basically, again, it's like sort of an intuitive relation that if small x, the value that we have here, is greater than e, that's fine. We have 1. This indicator will be 1, and we will be interested in the probability that big X is equal to small x. Otherwise, we get 0. And then we need to divide by, and this division comes from basically the definition applying the rule for the conditional probability. Then we divide by the probability that big X is greater than e. Okay, so this quantity here is given by this, and you can write it, of course. I mean, if you are interested that this thing is 2 cases, that it's probability big X equal to small x over x greater than a if x is greater than a, but if small x is less than or equal to a, this is 0. Okay, now what about the continuous case? So what, if I am required to compute a PDF, a conditional PDF on an event, like something like this, a conditional PDF on an event. Now, the problem with continuous random variables is that, something like this for a continuous random variable is 0, right? The probability that a continuous random variable is equal to a specific value, a singleton, as someone said earlier in the lecture, is 0. So for continuous case, like if you want to do things rigorously, you may start by actually studying the CDF and then differentiating. But it's always the case, I recommend actually that you use this trick, that if you have the continuous case, you can do the discrete case. And the discrete case, again, it has the advantage that you can write down these things without worry. And then after doing the discrete case, the continuous case is the discrete case. It is exactly the same as the discrete case, with PMF replaced by PDF. Okay, again, the rigorous way is the rigorous way, and I think maybe in some homework problem I will show you actually the rigorous way, just once. But it's boring. You start, you may start with the CDF, because the CDF has events that x less than or equal to small x, which is positive. But if you say big X and x is continuous is equal to small x, that event has probability 0. So it's problematic. But it turns out that again, continuous case is discrete case, and you take, so if this is the PDF of x given that big X is greater than 1, then it is like this formula. But here we have a PMF, the probability that a discrete random variable is equal to small x, converted into PDF. So this is the PDF of x evaluated at small x. Everything else is intact, indicator, and big X greater than a, big X greater than e. Okay, so so this is basically, it's like do PMF, do discrete random variables, replace PMFs by PDFs whenever needed. Okay, that's the shortcut. If you want to avoid basically getting the CDF first and then having to differentiate. Okay, so this is the PDF of X conditioned on an event. Okay, so again, in practice, we want to condition to have a conditional PDF on an event like this, or condition on another random variable, as we will see, and so on and so forth. So these things are all useful, and this is the first version of them. Okay, so the PDF of a random variable, a continuous random variable x conditioned on an event that x is greater than a, it's the PDF. You need to divide by the probability that big X is greater than a, and then you need an indicator here to tell you that if your small x here is less than or equal to a, then you should have a 0. Because if the event you are conditioning on tells you that your random variable is greater than a, then the conditional PDF, if you evaluate it at something less than a, should be 0. Okay, and this role will be played by this indicator here. And of course, you can like apply this to a specific, to a specific problem, like, the problem of, what if x is exponential? Okay, so you just plug in. So this is the PDF of x. Okay, so this is exponential lambda. This is the PDF of x. You put it here. And again, highly recommended that you keep indicators and so on. And this is the indicator that small x is greater than a. And then in the denominator, you need to compute this probability. And how do you get the probability in the denominator? The probability that big X is greater than a. Just integrate big, the exponential distribution with parameter lambda, integrate it from a to infinity, right? You integrate from a to infinity so that you get the probability that big X is greater than